Awesome. Well, we appreciate all of you joining today for Elijah's general exam. He has been doing a lot of excellent research for the last few years here at UW, and so we're really excited to see both what he's done and his finals. For the mechanical engineering, it mainly focuses on his final study and his kind of capstone project that he will be working on for the duration of his PhD. But Elijah joined us after getting his bachelor's and master's at the University of Dayton. He also worked at Booz Allen Hamilton in industry for a while, which is also where he built up his computational modeling chops. Airplanes versus humans, correct? Yeah,
a little different.
This morning, I also went back and read his original research statement and personal statement for coming to grad school.
Ooh.
And the very first sentence, though, was efficiency is captivating, which I actually find really interesting because, as you'll see today, he is ending up working a lot on energy and efficiency in humans. And I don't think he was quite planning on that at the time, or maybe he was. Maybe this has always been his dream, is to tackle human efficiency, but I thought that was really interesting. So we're going to turn it over to Elijah. He will give his presentation, and then we'll have a period for audience questions. So anyone can either unmute and raise their hand, or we have a group here too who can also ask questions. And then after that, he'll have the closed door session with just his committee. So sound good, everyone? All right, thumbs up all around. So we'll turn it over to you, Elijah.
Awesome. Thank you, Kat. The in-depth special intros are typically saved, I thought, for a dissertation. So I was going to make some bad joke that you could hype me up more, but I don't have to. That was awesome. Thank you so much. So thank you, Kat, for that intro. Thank you all for being here. A special thanks to my committee members, Dr. Steele, Dr. Manahar, Dr. Chen, and Dr. Althoff, as well as all of you for joining and listening today. Like Kat said, I will be presenting my general exam, which is essentially a culmination of what I have done, I'm currently doing, and what I'm proposing to do for the rest of my dissertation. My general exam is titled In Silico Techniques or Computational Methods to Elicit the Effects of Altered Motor Control and Cerebral Palsy. Technical difficulties? Okay. Can everybody give me a thumbs up that you can now see a child walking with the video? Awesome, thank you. So this is a child with cerebral palsy walking in what is commonly referred to as crouch gait. Now, cerebral palsy is a brain injury at or close to the time of birth that affects 3 in every 1,000 live births and currently affects over 750,000 people in the United States. Now, the primary result of this pediatric brain injury is altered motor control, which means an individual's ability to selectively control their muscles is impaired, which results in poor coordination and co-contraction. Now, impaired motor control often leads to secondary musculoskeletal impairments like bony deformities, muscle weakness, contracture, among a few. You'll hear me reference contracture a lot today, which is essentially a shortening or stiffening of a muscle. Now, complex interactions between impaired control and musculoskeletal system impart complex restrictions on mobility, making it very difficult to walk, like you can see here for this child. Additionally, they elevate energy. So children with CP consume at least 2 times more energy when walking, which increases the onset of fatigue, further limiting mobility. Now, a range of interventions exist to improve mobility in children with CP. However, they primarily target those secondary musculoskeletal impairments. And while they may efficiently or efficaciously address those and improve gait kinematics, they fail to improve motor control, again, which is that primary injury in CP, and they fail to reduce energy consumption, resulting in only about a 50% rate of functional improvement after these interventions. Now, poor treatment efficacy results in follow-up, necessitating follow-up procedures, which increases emotional and economic burden on patients and their caregivers. So if I haven't emphasized it enough, let me state we got to do better. So how do we improve mobility in CP? Well, if we look at literature, we would see that function is actually associated with energy during walking and motor control, or the severity of their motor control impairment. In that individuals who consume more energy when walking have lower levels of function, as well as individuals who have more severe motor control impairments have lower levels of function. Additionally, individuals with more severe motor control impairments have worse treatment outcomes. So maybe it is then more apparent or obvious if we remain unable to treat these primary correlates or determinants of function that may underlie poor treatment efficacy for children with CP. Now, you're probably thinking, okay, Elijah, why don't we just treat those? And while I don't disagree with you, random passionate listener, I'm probably oversimplifying things. It's not that these interventions don't attempt to improve energy during walking or alter motor control. It's that they remain unable to because CP is incredibly complex. So let's consider something like energy during walking. Let's say we want to reduce a child's energy that they consume during walking. So we need to account for all the functions and variables at play in a child with cerebral palsy. So that starts with our primary motor control impairment, again, which leads to secondary musculoskeletal impairments like contracture, weakness, spasticity, and bony deformities. Next, we would consider how they walk. So gait kinematics, as well as their walking speed, and how the impairments influence both of those, and actually how those two interact. Lastly, we would account for anthropometrics and characteristics like mass, age, height, and sex, and how things like mass, height, age, and sex can influence strength, as well as walking speed and gait kinematics. And then finally, we would have all our factors, and we can examine how they influence energy during walking. And when we look at this, it becomes very apparent what we have to do, right? If we want to reduce energy during walking, what we would do, we would shoot, maybe it's not so easy, but that's the point, right? The CP is incredibly complex. And experimentally, even in non-disabled individuals, we have extreme difficulty isolating one of these factors, changing it, and examining how it affects some outcome. Now, if only there was some way to isolate these factors and have true controls and examine their effect on an outcome. Does anybody know any methods for that? This is an interactive generals, so these aren't rhetorical questions. I can wait. Yeah, modeling and simulation. Thank you, Alyssa. Right. So modeling and simulation enable rapid causal analyses. So we can have true controls and isolate factors, alter them, and examine how they affect some desired outcome. Additionally, modeling and simulation allow us to predict difficult or immeasurable quantities. You'll often hear me refer to them as in vivo quantities, which means within the living. These are things like muscle forces and joint contact forces, which provide additional informative data for analyses and validation. This is why I believe physics-based modeling and simulation are perfect for investigating altered motor control and energy in CP. So imagine our child with cerebral palsy. With modeling and simulation, we can isolate things like motor control, gait kinematics, and how they influence energy during walking. This would look like modeling unaltered control, generating a gait simulation, and then predicting energy from that simulation. We could then impair control in our model or alter motor control, generate some new gait kinematics, and have a new energy prediction. And this has been a good deal of in silico research in CP. They have mainly investigated how musculoskeletal impairments influence gait kinematics, or how gait kinematics that children with CP often exhibit influence muscle demand. However, they don't incorporate that primary motor impairment, and they fail to correlate to energy during walking. Now, there have been two prior studies that actually have incorporated altered motor control. One was a case study of a single individual, and another one perturbed altered motor control and examined how it affected gait kinematics and energy during walking. What they found was that altered motor control can prevent non-disabled gait and elevated energy during walking. So at some point, a motor control impairment can become severe enough, preventing an individual from walking in a non-disabled manner. And with each step in severity, we saw an increase in energy. So this kind of emphasizes how altered motor control can drive gait deviations and energy. But again, we don't have that complex interaction between musculoskeletal and motor control impairments. Now, it'd be ideal if we could essentially extend this study to incorporate those musculoskeletal impairments. So if we take a glance at who did that study, it's like a perfect game of Clue. Dr. Marabi with Dr. Steele at UW. And if this doesn't perfectly set me up to do the follow-up of this study, then I don't know what is. So for my dissertation, I'm asking if in silico techniques can be used to elicit the effects of altered motor control on gait and energy in CP. Now I've split my dissertation into two sections, which we'll cover today. The first being what I've completed or what is in progress, and the second being what I'm proposing to do to complete my dissertation today. Now in that first section, I'm using modeling and simulation to quantify the impacts of altered motor control on gait. My first study resulted in a publication titled "The Number of Synergies Impact Sensitivity of Gait to Weakness and Contracture." My primary questions during that study was, does altered motor control increase sensitivity of non-disabled gait to weakness and contracture? And does altered motor control exacerbate energy demands required to adapt to weakness and contracture? In short, in the presence of weakness and contracture, does altered motor control make it more difficult to walk in both a non-disabled manner and with relation to energy? So before I introduce any of my methods, I have to introduce my good friend, Jerry. Can everybody wave hi to Jerry? I'm assuming everybody online waved, so I appreciate that. So this is Jerry. Jerry is my good friend. He would wave back, but he doesn't have any arms because Jerry is a sagittal plane musculoskeletal model with a hat, which is a combined head, arms, and torso unit. So it's a torso with increased weight. Additionally, Jerry has 2 thigh, 2 shank, and 2 feet, giving him 9 kinematic degrees of freedom. Now, each of Jerry's legs is actuated by 8 hill-type musculotendinous units, which then actuate his 9 kinematic degrees of freedom and allow Jerry to walk forward and backward and up and down. Additionally, we model ground contact with 10 continuous Coulomb contact spheres, which allows to actually predict ground contact forces, meaning we require very little experimental data to simulate gait. So in order to simulate a gait pattern, we extract Jerry's dynamic equations of motion and feed them into a direct collocation optimal control framework, which is a mouthful for essentially a trajectory optimization, meaning we are asking Jerry to generate a desired gait pattern while he minimizes some objective function. Now in this Jerry's framework, we have 2 terms in our objective function. One is a tracking term, which we ask Jerry to replicate a desired gait pattern by minimizing the deviations from those kinematics. And then we have an energy cost term where we ask Jerry to walk in an energy efficient manner. Now, lastly, before we start simulations, we need things like initial guess to initialize our optimization, as well as things like muscle parameters. With that, we can generate optimal neuromuscle excitations and generate this optimal gait pattern or our simulated gait pattern. Now, what is unique about Jerry is that he has modular control. So we can alter the number of muscle synergies, which is correlated with motor impairment severities, as we reduce the number of synergies controlling each leg to simulate more severe motor control impairments. Essentially, we are constraining the dimensionality of Jerry's control. This is what the previous study that I mentioned that Nasser did, was he tracked non-disabled kinematics and he altered motor control. Again, finding that motor control impairments can prevent non-disabled gait and elevate energy during walking. But again, this misses the complex interactions with musculoskeletal impairments that children with CP often have. So what I did was incorporate this loop where after we generate a simulation, we examined if it sufficiently replicated the desired kinematics. If it did, I then simulate muscle weakness or contracture, and I iterate through a range of altered motor controls and contracture and muscle weakness severities until we reach a point of failure, essentially where Jerry was unable to walk in a non-disabled manner. At that point, we consider it a point of failure or an impairment threshold. And what I'm investigating is how altered motor control affects those weakness and contracture thresholds and the energy, the required energy, the rate at which energy increases with each impairment. So let me orient you before we dive into a bunch of pretty colors and bars. So on the bottom, we have our weakness scenario. So this is a muscle I am weakening. We have our weakness threshold. That is that point of failure. It's a % reduction in maximum isometric strength. So we have higher values indicate less sensitivity to that musculoskeletal impairment. Lower values are more sensitive. So a quick check on everybody's retention and who's awake. On average, and we have in darkening purple more severe motor control impairments. On average, more severe motor control impairments are less sensitive or more sensitive to weakness. Only one thumbs down. Okay. Thank you. 2 thumbs down. Less sensitive. Sorry, I can't see everybody's cameras online. Yes. We found that on average, more severe motor control impairments are more sensitive to weakness scenarios. And we actually saw that across all of the weakness scenarios we had. So altered motor control is affecting sensitivity to weakness, with the trend being that motor control impairment severity correlates with muscle weakness threshold. Additionally, with our contracture scenarios, we see the same thing. Altered motor control affects sensitivity to contracture, with more severe motor impairments decreasing that threshold, indicating higher sensitivity. So in conclusion, we found that motor control impairments increase sensitivity to weakness and contracture during non-disabled gait. Does this seem intuitive to anyone? Right, we simulate one impairment, we simulate another one, it gets worse. What's the BFD, right, Elijah? While I don't disagree with you, that's not the whole story. So we're showing very complex interactions between altered motor control and these musculoskeletal impairments. And they're having a nonlinear effect, and that nonlinearity is actually pretty important. And we can use something like this to inform treatment precedents. So if we look at something like hamstring weakness, and we consider achieving a non-disabled gait pattern as our intervention goal, we can see those large deltas with motor control. So motor control appears to be a primary driver of preventing non-disabled gait with hamstring weakness. So if you were treating an individual with both hamstring weakness and a motor impairment, it may be more efficacious to treat the motor impairment rather than hamstring weakness. But we see a different story when we look at things like soleus and plantar flexor weakness, because there's little to no difference between those impairment thresholds. In that case, it may actually be more efficacious to treat the weakness of the plantar flexors rather than the motor impairment. So I didn't only look at sensitivity, I also looked at energy consumption. So here we have an increasing musculoskeletal impairment. This is hamstring weakness. And on the y-axis, we have energy consumption. Now, each simulation, we predict a new value of energy consumption. And again, in darkening purple, we have more severe motor control impairments. Those X's denote the points of failure. And you'll notice, probably intuitively, that as musculoskeletal impairment increases, we see an increase in energy required to adapt and maintain that non-disabled gait pattern. But the rate at which that energy is increasing is different and is control sensitive. So to analyze that, we fit quadratic polynomials to them and examine their second order coefficients. Now those second order coefficients essentially tell us the rate at which energy is increasing with that musculoskeletal impairment. And higher second order coefficients indicate that the individual is having to exert more and more energy to maintain that non-disabled gait pattern. So again, looking at our weakness scenario, we have that second order coefficient. On average, motor control impairments had higher second order coefficients, indicating that an individual with a motor impairment has to exert more energy in order to adapt to weakness. And that story remained true across all our weakness scenarios and all our contracture scenarios. So we're seeing that altered motor control affects the energy required to adapt to both weakness and contracture. Yes, Dr. Manahar. So we use root mean squared error threshold on each of the kinematic degrees of freedom. So ankle, knee, and hip, tracking the non-disabled kinematics. So when it deviates past a single degree of root mean squared error, we consider it a point of failure. Good, great question. And the trend we're seeing is that motor control impairment severity increases, so does the energy required to adapt to weakness and contracture. So motor control impairments exacerbate the energy required to adapt to weakness and contracture during non-disabled gait. Again, that nonlinear component being very important, but it appears here that motor control impairments are primarily driving energy required to adapt to weakness and contracture. So my big takeaways were that altered motor control increased sensitivity to musculoskeletal impairment, and they exacerbate the energy required to adapt to musculoskeletal impairments. Now, these are likely gait sensitive, which leads me to my next study, where I'm asking if gait patterns commonly seen in children with CP are advantageous. So my driving questions behind what I'm currently doing are, during CP gait patterns, does altered motor control decrease sensitivity to weakness and contracture? And does it actually decrease the energy required to adapt to weakness and contracture? The same framework. What I've now changed is we are now tracking common gait patterns in children with cerebral palsy, and we are again analyzing the same outcomes. So this is in progress. So I only have a couple results, but so I'm simulating two motor controls. We have unaltered motor control, and then in dark purple, we will have severely impaired control. We're only looking at gastrocnemius contracture, and we have both non-disabled gait and severe crouch. So if we look at our contracture thresholds, the non-disabled gait pattern is what you saw prior, but now we're seeing that in severe crouch, typically thought to be a very inefficient and suboptimal gait pattern commonly seen in children with CP, is actually more robust or less sensitive to gastrocnemius contracture. Additionally, we actually see a negative value for our second order coefficient, which means that in severe crouch, as gastrocnemius contracture increases, energy is actually decreasing. So the gastrocnemius contracture appears to be severe crouch appears to be energetically advantageous in the presence of gastroc contracture, even with a motor control impairment. So again, this is only for a single gait pattern seen in CP and only currently gastrocnemius contracture, but we are seeing that severe crouch is reducing sensitivity to musculoskeletal impairment and reducing the energy required to adapt to that musculoskeletal impairment, indicating that CP gait patterns may be less sensitive and are energetically advantageous, even in the presence of motor control impairments, to very specific musculoskeletal impairments. Now, something that's important is that motor control impairments, this remains true in the presence of motor control impairments, but those motor control impairments are reducing essentially the magnitude of that advantageousness. So we're still seeing an increase in sensitivity and actually a decrease in that energetically, severe crouch being energetically advantageous. Now, again, this is underway. I'm going to simulate more motor control impairments, so have a larger grid, as well as additional weakness and contracture scenarios. And then I'm going to incorporate other CP gait patterns. So this will be a range of crouch, mild and moderate crouch patterns, as well as things like true equinus, flat foot, and then a mixture of both crouch and equinus. I'm expecting to find that CP gait patterns are advantageous in the presence of motor control and musculoskeletal impairments, which is actually pretty important considering gait patterns in CP are typically thought to be energetically suboptimal and inefficient. So if we consider the impairments present, it may indicate that the individuals are still optimizing energy and that we should account for their impairments when trying to reduce energy. So my studies, along with previous in silico studies in CP, have done a pretty good job at eliciting these complex causal relationships, as well as predicting those in vivo quantities. However, these studies fail to translate to a clinical setting and inform clinical practice, which for a computationalist like myself is a little saddening. But why is that? You probably want to bring up the elephant in the room. And while I hear you, and I have put on some weight during COVID, I don't appreciate you calling me an elephant. No, it's the fact that Jerry isn't a child with CP, right? Our models aren't exact representations of the dynamical system we're measuring or examining. But there's been a recent field of research that indicates this may not be as big of an issue as previously thought. So who here has heard of discrepancy modeling? I thought there'd be a lot more people here. Wow, a couple people. Mainly people in my lab, which makes sense. It's a new field. So I believe there's a single publication on discrepancies in biomechanical studies by the Steel Lab's very own Megan Ebers. She's in here. That's her shout out. So what discrepancies are, or discrepancy modeling, is we have some dynamical system, we measure it, and then we try to represent it with our model. However, there's inherently some delta between the two. So this is the difference between measured data of a child with CP and what Jerry actually represents and replicates. Now that delta or difference is the discrepancy. And what Megan used was machine learning to analyze this discrepancy and examine response to exoskeletons. What she found was that discrepancy was learnable and informative and actually improved predictions of exo response. However, there was still some delta, so some missing ability to fully predict exo response, which indicates that the data we have, and what Megan used was clinical gait data, so 3D motion capture data, as well as EMG, may be insufficient, either in volume or information. So the data we collect may not encode response, which is pretty important. So if we understand that the difference between Jerry and a child with CP may be informative, then what limits translation? And perhaps in my mind, a larger limiter is that prior studies scope only examine small stratifications or subpopulations of children with CP. So myself and others may simulate a single individual, or if I simulate multiple gait patterns, we are essentially looking at 4 to 5 individuals with CP. But in fact, CP by definition is heterogeneous. So we are constraining our investigations and our translation by only looking at small subpopulations, which I believe likely underlie translation and even poor treatment efficacy, like we discussed earlier. So there's a need to use robust large-scale analyses to understand and treat motor control and elevated energy in CP. Now, if only there was some method. I was really good with complex data and ran on a large scale. Dr. Manahar, would you happen to know any? Machine learning, that's right. So machine learning is perfect for high dimensional, nonlinear, and heterogeneous data, which is human movement data. However, it lacks causality and interpretation, which limit translation and actionable insight. Q modeling and simulation, which again permit these rapid causal analyses. We can isolate A and examine how it affects B. But like I just mentioned, we typically only work with small stratifications or subpopulations, so there's a need for large-scale population-wide analyses. Bring it back to machine learning, which, like Dr. Manahar suggested, is perfect for large-scale analyses of heterogeneous data. But machine learning necessitates big data being both population representative and sufficiently informative. Now, we can use things like clinical databases to hopefully encapsulate the population representative factor. However, like I mentioned earlier with Megan's study, it is still a question if our data is sufficiently informative. So the easy response would be collect more data. But like follow-up procedures, additional collections for children with CP increase emotional and economic burden. We can throw that right back to modeling and simulation, which are fantastic for generating additional informative data at little to no cost. So these can be immeasurable quantities or these rapid causal analyses. So who's starting to see the picture here? But it wasn't that picture. So it's not, in my mind, is not a question of which computational method is better. It's that they're actually perfect for each other, right? We can feed off, each one can feed off each other's limitations and apply a benefit. And this is essentially what I'm proposing to do for the rest of my dissertation. So I'm proposing to combine modeling and simulation, as well as machine learning, to identify the effects of altered motor control on energy and CP. For the first aim, I'm going to quantify causal mechanisms underlying elevated energy in CP, and then evaluate clinical and synthetic data being generated from simulations, ability to predict energy during walking in CP. For aim 1, I'm asking, can simulated data elicit causal mechanisms elevating energy in CP? And are motor control impairments the primary causal mechanism elevating energy? Big, beautiful picture or scary, up to you. But we'll cover each section. But in short, I'm going to use a clinical database, generate big simulation data, and then use machine learning to extract those causal analysis or the causal mechanisms. So for the clinical database, I'm using a database from our clinical partners at Gillette Children's Specialty Healthcare, which is one of the largest databases for children with cerebral palsy. Within the last 20 years, they have about over 6,000 children have come through with cerebral palsy, and they have data for it. Now, in order to simulate gait, I need individuals who can ambulate. So these are individuals with GMFCS levels 1 to 3, who've had 3D motion capture data, as well as a 6-minute energy test, which gives us that measure of energy consumption. So after looking through all the individuals that have completed both motion capture and the energy test, we have a little over 1,000 children with CP. Now we have a ton of data from 3D mocap. We get those gait kinematics, as well as lower extremity EMG. We have clinical measurements of spasticity and strength, as well as motor control, both selective and dynamic. And then from that 6-minute energy walk test, we have breath by breath oxygen consumption and a non-dimensional normalized energy consumption value. Now for my first aim, I'm proposing to use both the gait kinematics and the non-dimensional energy consumption. And what I'm going to do is feed those gait kinematics into my Jerry framework. So this will be the kinematics that we asked Jerry to track and then generate a gait pattern, which will give us one baseline simulation for each child. Additionally, the beauty of modeling and simulation is that we can perturb and isolate mechanisms. So I'm going to simulate or perturb a grid of 30 motor control and musculoskeletal impairments to generate 30 perturbed simulations. Now what this grid looks like is 3 motor controls. So we have unaltered control, impaired control, and severely impaired control. Again, we're reducing the number of synergies to simulate motor impairment. And then we have weakness or contracture in the hamstrings, plantar flexors, gastroc, or tibialis anterior. Now, how did I choose these impairments specifically? So they're commonly reported in CP. They are common targets of interventions. They've been shown to alter gait and energy. And I'm effectively altering at least a single muscle that crosses each joint. I'm going to head off a bunch of questions that probably arise with this. So we have exam data for some compartments or specific muscles that give measures of contracture, spasticity, and strength. Am I planning to use those? No, I'm not. What about muscles that cross the hip? A very astute observer may identify that it appears we are not affecting any muscles that cross the hip. However, Jerry's hamstring is biarticular, so it crosses both the hip and knee. So we are affecting a muscle that crosses, at least a single muscle that crosses the ankle, hip, and knee. So if I'm simulating this predefined grid of impairments, rather than their actual clinically measured impairments, how does this help? So the clinical measurements would essentially provide us with a single data point. And the point that I'm trying to emphasize is we may need more data, which this permits. Additionally, each one of these, this grid can essentially provide additional information. So if we think about energy predictions, we have a baseline simulation. And once we simulate impairment, that energy prediction goes up, goes down, or remains the same. And the magnitude of the increase or decrease, the magnitude of increase or decrease, I believe, are extremely informative as well. So if you consider something like gastrocnemius contracture, which is very prevalent in CP, for an individual who toe walks or in true equinus, gastrocnemius contracture will likely reduce the energy consumption prediction. However, if we simulate something like quadriceps weakness in crouch gait, which is known to increase the demand of the quadriceps, we're going to see a very large increase in our energy predictions. And lastly, that no change could be things like rectus femoris weakness in non-disabled gait. It's been previously reported that the rec fem, when weakened, essentially has no effect on energy. We see this experimentally that non-disabled individuals don't really use their rectus femoris during gait. This isn't to say biarticular man that you don't need it, but our system appears redundant enough to not require the rectus femoris during non-disabled gait, or that weakness in it does not affect energy predictions. So I think this encodes a ton of additional data where we don't actually necessitate the clinical data. So with that grid of 30 perturbed simulations, we will then have 31 simulated energy costs which we can subtract off our experimental energy consumption value and get 31 energy discrepancies. Now we will feed all of that data into a machine learning algorithm, and I'm going to use what is known as BART, Bayesian Additive Regression Trees. Now BART is a summation of regression trees for non-parametric function estimation that uniquely relies on Bayesian probability. For those of you not in machine learning, that's essentially gibberish. So we have regression trees or decision trees that essentially represent decisions that then parse the data. And what we do is those regression trees are built in that they are weak learners. So we have a branch, we ask if it's essentially above or below some value, and then we make another decision and a prediction. Now, weak learners accurately predict a very small portion of the data. However, when predicting all of the data, each one would essentially poorly predict the test data, which is why they're weak learners. But the summation of them is stronger than each individual part. Now, what's unique about additive regression trees is they can be very accurate. However, the difficulty is determining the number of branches or leaves that the regression trees have. So you could essentially have infinite number of trees, or you can have a branch or leaf for each data point, and it would essentially act as a lookup table for some value. So you've hyper-tuned or overfit your tree. So you need some way to optimize the number of branches or leaves, which is where this prior comes in from BART. So it optimizes the number of trees, or it's called a regularization prior. Now, BART is fantastic because it allows for interpretability, interactions effects, and causality. This is starting to become very prevalent in biomechanics in its ability to replicate or predict, experimental measures as well as infer causality. Now, in order to get at causality, we need a causal model, which I'm going to refer to as DAGs here, which are directed acyclic graphs. Now, who here has seen DAG? One person. Trick question, you've all seen a DAG. We can clean it up a little, and this is what a DAG actually looks like. So DAGs force researchers to consider all the factors influencing the response. And then DAGs represent the hypotheses and assumptions about mechanisms affecting the response. So within a DAG, we can incorporate things like unmeasured factors, predictors, potential confounders, and response. And there have been 2 prior studies in CP that have incorporated BART as well as DAGs, and they've found that altered motor control was a primary determinant of gait deviation, pre-intervention gait deviation index, which is gait kinematics. Another found that GDI was a primary determinant of energy consumption. So my hypothesis is cutting out this middleman. This is too many hops for me. And I'm hypothesizing that altered motor control is the primary causal mechanism driving elevated energy consumption in CP. And what I'm proposing to do is to address that idea of data insufficiency, where we may not have enough data for each individual, and use modeling and simulation to perturb each one of these theorized predictors. So again, we can simulate motor impairments and examine their effect on our energy predictions. And with machine learning, we can then elicit or identify those primary causal mechanisms elevating energy. So after we run BART, we interpret our results very visually. These are known as accumulated local effect plots, or ALEs, and they show our change in predictor versus our change in response, which is again where I'm predicting that altered motor control is primarily driving energy. So again, I'm expecting to find that modeling and simulation enable machine learning to highlight that altered motor control is the primary causal mechanism elevating energy in CP. Now in AIM2, we're going to focus on predicting, and I've mentioned important aspects of this, but I want to just address it explicitly. If we can predict, we can understand, we can address the need of measurements. That is, we can address the need for infeasible experimental measurements, and then we can test the efficacy of treatments prior to the intervention. So if we can predict things like energy costs, we can perturb our predictions and hopefully inform interventions. Now, what I'm proposing to predict again is energy. And hopefully I've conveyed how important it is, but I like this quote Energy consumption during walking is of fundamental importance to the body's health, fitness, and physiological status. And currently, even in non-disabled individuals, we can accurately measure energy, but we fail to predict in the absence of those direct measurements. And those direct measurements are impractical to collect. In all of these, the importance of energy during walking, our inability to predict, and the impracticality of direct measurements are further amplified in children with CP. So we don't understand elevated energy in CP. We currently are unable to predict elevated energy in CP. And the direct measurements, that 6-minute walk test, is extremely feasible for children. So many children with CP are unable to walk for 6 minutes to actually get that energy measurement. So there's a need to accurately predict energy in CP using very limited clinical data, which in my mind is a bad signal for Jerry or a signal for machine learning or modeling and simulation because it can provide additional synthetic data at little to no cost. So during AIM 2, I'm asking if simulated data can complement clinical data, enabling better energy predictions. Then I want to examine what data have the largest effect on energy predictions. So for this AIM, I'm going to actually use 3 BART models, one that uses wholly clinical data, one that uses wholly simulated data, and a hybrid model that actually uses both. And we'll examine prediction accuracy as well as the primary predictors or effect size. So I'm going with the kitchen sink approach, which is essentially use all the data we have in hopes to get the best predictions. Now for our clinical model, I've covered some of this before. We have strength and spasticity measures, which I will use of the 6 muscles or the 6 different muscle groups we have, as well as summary metrics of both. Additionally, I plan to use characteristics and anthropometrics like height, age, mass, sex, and walking speed. Then I'm going to incorporate clinical gait analysis data. So we can still use summary metrics like GDI, as well as these clinical measures of motor control, but I want to focus on incorporating kinematics and experimental EMG. So we have to use discrete metrics with BART, so it's important to incorporate measures that both differentiate different gait patterns and control strategies. So this will be using things like joint angles, translations, as well as their derivatives, splitting those into stance and swing phase, and then looking at minimums, maximums, averages, as well as values at initial contact and toe off. Now, very similar for experimental EMG, in order to examine different control strategies, we'll then split into stance and swing phase and look at peak activation as well as the integrated activation to show a change in maximum activation and time active. For our simulated data, we will have our simulated impairments as well as all these simulated gait patterns. We're using the same measures of kinematics, and now with our predicted excitations, we're processing them very similar to the experimental EMG. However, we can now incorporate things like the energy discrepancy, which I mentioned before, how I believe it can be very informative, as well as things that are unmeasurable, those in vivo quantities like MTU dynamics. So this can be contractile velocities, tendon, muscle belly lengths, all of which I believe can be informative. Now, what I'm hypothesizing is that the model that uses both, our hybrid model, will most accurately predict energy. But what is cool in additional analyses is similar to sparse sensing. Now, machine learners, Dr. Manhart, don't get mad at me, I know it's not sparse sensing, but we can essentially identify what is primarily driving our energy predictions, and we could use those to inform clinicians of what is necessary to collect, hopefully reducing clinical burden. So this could be things like kinematics, as well as clinical motor control, and maybe MTU dynamics. I'm expecting to find that simulated data does complement clinical data and clinical motion capture data and exam data to improve prediction accuracy of energy in CP. Now, by the end of this, I'm hoping to have both theoretical and translational. I'm aware of in silico studies and how they are limited, so this may be the computational realism or pessimism, but theoretically, by the end of my dissertation, I will have quantified the effects of altered motor control and non-disabled gait and CP gait patterns. I will improve the understanding of primary causal mechanisms elevating energy in CP, and I will have demonstrated in silico techniques that and Silico techniques can elicit additional information to inform future investigations. Computational optimism, it would be fantastic if this translates to a clinical setting in demonstrating that gait simulations can be used to inform treatment precedents. Altered motor control is the primary causal mechanism elevating energy in CP. And lastly, in silico techniques can be combined with clinical data to create and develop clinical evaluation tools. I have an accelerated timeline. I'm hoping to do this all within a year. And with that, I would like to thank my previous PIs, my current PI, as well as everyone in my lab, mentors, collaborators, friends, and family. I couldn't have done it without you guys, so thank you. And at this point, I'll accept questions. Yeah, I'm trying to find my mouse real quick.
Did you say there is a 2D model, and that's what you plan to use for the future simulation?
Correct. Yep.
I know that some of the muscles they talked about like abstract, but they're also active in the frontal plane.
Yes.
So those frontal plane effects won't show up in your simulations.
Correct. Yeah. So,
What do you think? Yeah.
so the easy answer or the default hope is that maybe discrepancy encapsulates that. However, that's definitely true. We may not capture 3D or out of plane kinematics, which are actually pretty common in CP. We may show that it's not necessary or it's in our discrepancy. I think if we find that altered motor control or essentially we don't find with Jerry additional information, I think that would indicate that something like out of plane kinematics and control are very important. So this could be things like stability, which is very hard to quantify in silico, but maybe driving their elevated energy. Additionally, we don't have to commit to Jerry. Before I delve into the entire clinical database of simulations and generating all these, I will do some smaller studies with a smaller group of children with CP. And we can use things like OpenSim, which have validated 3D models and work from there. Yeah, great question. Anybody else? Kim.
In the hybrid model you proposed, it seems like it has redundancy in the gait kinematics, both simulated and experimentally collected.
Right.
Do you expect that those would give individually informative data, or if they would be just source where you could rely on them?
Yeah, so Kim asked, in the hybrid model, we will use both experimental kinematics and simulated kinematics. And is that redundant? So we are tracking kinematics and asking Jerry to walk in an energy efficient manner. So we do not perfectly replicate experimental kinematics. So we could get some difference there. So I think they both could be informative. One of the advantages of modeling and simulation is experimental data, we have noise and error, right? So with that data may not perfectly represent a physical model. However, Jerry is simplified, but he's built around physics. So we do encode physics principles into a simplified motion. So I think that difference could still be informative, and that's why I plan to use both. Great question. No questions online. Alyssa. Mm-hmm.
Like, how are you actually quantifying?
Yeah. So we're using a validated, it's like a muscle probe. So what it does is you essentially gather, length, activation dynamics, all of this, and it predicts energy consumption. So there are a couple metabolic cost probes that are out there. There's the Umberger 2010 as well as the Margrava 2004. And they've both been experimentally validated and accurately replicate or predict non-disabled gait energy. So I actually already have the Umberger metabolic probe built. We could use that other one. And then essentially what we do is use that probe after the simulation's generated, and it will generate a value of energy consumption. Does that make sense? Yes, yes. Yeah, I've seen it used. So the single case study, the child with CP was Antoine Felice and Friedel de Groot, and they used that energetic probe, and they got, what's the classic simulation term? Like we accurately predicted the waveforms, or I'm forgetting the term, I apologize. So it was close, and what they were able to use was actually that to examine, again, energetic efficiency. So they got similar values for a single gait pattern for a single child with CP, but again, limited in the population spectrum. So that question still does remain if it's accurate for replicating gait patterns in CP. But currently we can't predict energy. So I think we're coming at the problem from just a different angle. So having like two discrepancies, essentially?
Well, just like how much of that discrepancy is
Oh, so how much is the actual energetic probe influencing that discrepancy? That's a really good question. So I haven't seen that reported before, but what we could start with would be non-disabled gait and use that metabolic probe, and I actually have. So we could compare that to the experimental measures or literature and see how far off we are. And that would give us insight on maybe how far the probe's estimates are off. That could still be gait specific, so I'd have to consider that more. That's a really good point. Anybody online?
No more questions from the online gallery? All right, well, let's see. So I think if everyone will join me in once more, giving a good job to Elijah, round of applause. All right, at this time, we will now kick out of the room and out of the Zoom room, the non-committee members. So thank you all so much for joining, and we'll wish Elijah best.
Thanks all.